All right. So here's what's gonna happen. So your exam is gonna be a little bit of 19, no, let me get the right one. A second. So this is exam 3. And again, we're gonna just do this a little bit differently just because it's not a ton of material. And in any case, really, you guys are kind of getting killed on the multiple choice anyways. Yeah. No, I'm not. It's, that's kind of where like the, yeah. All right. So the reactions that I said you needed to do that we kind of did at the end was that you could do, so we had those so we had a Grignard, so this is chapter 20. You had the Grignard plus carbon dioxide. And then you did the HCl and water, and that gave you a carboxylic acid. Okay. Where the carbon comes from the carbon dioxide, okay? You could see this, I just want you to understand, like this comes in a couple of different forms, right? So you could see this in the context of making the Grignard. And I'm giving you this because from a synthetic perspective, okay? So let's just say you have, and this is super simple, okay? An alkyl halide. And you have to make that carboxylic acid, right? So you have to, again, it is an old reaction in that it wasn't from this chapter, but it's this semester, right? You know how to make a Grignard. So your first step is the magnesium and ether. And then your second step's adding carbon dioxide. And then the third step's the HCl in water. So I just want you to understand. So even though this is the new reaction, you have to use what you have previously, right? How to make the Grignard, okay? All right. So that was one. Another one that we did was with the esters, right? I showed you how to reduce an ester. So it's either DIBAL or sometimes you see it with the H. And that will take an ester and reduce it to an aldehyde. If you reduced with lithium aluminum hydride, that takes you all the way to the primary alcohol. And then the other couple of reactions that we did involved your nitriles. So you can make a nitrile by doing an SN2 reaction, right? So that you have your alkyl halide. You treat with sodium cyanide and you get your nitrile. And then what we did was we did 2 reactions with these nitriles, where if you take a nitrile and you add a Grignard reagent, you get a ketone. And then the other reaction that we did was a reduction, which I think I did anyways in the beginning of chapter 20 when we did those cyanohydrins, but just to kind of emphasize it again. So you have your nitrile and you treat it with lithium aluminum hydride followed by water, and you get an amine. Okay. AJ.
What does it say after the sodium cyanide?
Oh, so it's R, you know. You get the nitrile there, okay? It's just a substitution reaction. It's just SN2. All right. So that was from your chapter, like those little bits from chapter 20. Right. So the format of this for your exam, all right. So again, exam 3, it's going to be in class, no take home. Right. It's going to be all part 2 type questions. You can use your notes. You can have a laptop. So you can have some type of electronic device, okay? Yes, Chris. Okay.
I don't like how to sound.
All right. You can have some type of electronic device if you need to look stuff up. All right. Clearly, all right, there will be no texting each other. Like, what do I do? Okay. Again, I'm gonna just, you say it takes balls, but a lot of you have them, and I just don't get it. I don't get it, but all right. I'm just gonna say, like, I'm not, you might think you get one over on me, but you have to be clear. While I love a true Cinderella story where someone all of a sudden gets it, it's very few and far between, okay? So if all of a sudden, now that I'm giving you these resources and you're in class versus at home, you weren't doing well on the part 2s, and now we have some miraculous, I'm doing well on part 2, like, I'm gonna think twice, okay? So in these directions, I'm gonna put the same thing that I put in online. If I suspect you of cheating, I reserve the right to make you do a whole new problem in front of me, right? That's because I know with AI, I know there's just ways to do these things. And if you feel like that's the way you have to go about to accomplish this, then I have every right as your professor to hold you to academic integrity, okay? All right. So with that being said, and we have this recorded that I'm saying this as well too, okay? Like, if you cheat, all right, I have the right to have you do the question, at least do the question over in my presence, like not even give you a new question just to see if you actually can do it, okay? All right. So with these part 2 type questions, you are going to have an NMR question, right, that has a mechanism. So very similar to like what your part 2 was. Okay. You're going to have a reaction sequence. Okay, so that whole A, well, sorry, I give you that one. So it's where you figure out what A is, to B is, to C is with that starting material. Okay. Then you are going to have a page, and you know what, this is going to be this is how your final is going to be laid out too. Okay, so just, it's not like I'm not going to use this format again. Okay, then you're going to have a page where it's just fill in the box, where it's just isolated reactions. And then 4 will be your synthesis. And 5 will be the circle of the compound. The only problem that might have a little bit of chemistry from previous chapters is your synthesis, okay? This is the only one that might have, and I'm talking this semester. I won't pull from the fall like I have reserved the right to in the past when you take it home, okay? So this is the only one that might have a reaction from I would say from what 18, 19, or 20. Okay. That's the only one.
Like
Right.
circle the compound means like which one?
Which one's more reactive? Which one's more acidic? Yeah, Grace. Yes. Did I not?
No,
I did.
I never saw it. It's under the
Yeah, pretty sure I did.
It's like the.
I think I did two, right? Like, I think I did two. I think I did a static key and then one where I spoke.
Yes.
Usually you don't, like, sometimes you guys get announced, like, I don't announce everything because half the time some of you tell me that every time I put a file up, you get a ding, so I just. Yeah, so, yeah. All right, yeah, but if you can't find it, then I'll put it in an announcement, but it should be in the module. Okay, so.
Oh, yeah.
All right, so this is that's how it's gonna be laid out. The other thing that I will do, okay, is the synthesis will be only 10 points, okay? Because I know that's like one of the harder things for you guys. So keep that in mind, okay? But that means your points are gonna be spread out more. So like that NMR mechanism question's probably gonna be like 20 to 25 points because it's a mechanism you have to go through and show me the electrons and everything. Okay. All right. All right. Does anybody have any questions as far as this goes?
In
Agent?
any NMR problem, if there's two blanks, we have to figure out the product and the starting material.
Correct.
If you get the starting material correct, do you even have to like do the NMR process for the second one?
No.
Or you just do the mechanism?
Correct. Okay. But but you can use the NMR to check your work. Like that's what I would do. And I've said this over and over again. If you, let's just say you have something where, here, I'll give you what I was thinking for like a practice. No, don't want to do that. Hold on. Okay, so. All right. Just give me a sec. I got to simulate the NMR again. I have it all on another screen, but then you'll just see the whole answer. Okay. So you could do the degrees of unsaturation while I'm writing this stuff out. I have to just give me a second. Once you guys get that down, I have to just turn my screen share off for a minute and look at my notes. All right. I'm just gonna, just give me a moment and then. All right. That doesn't sound like you're working on this NMR structure. It sounds like you're talking about your structure. So why don't you focus and work on the NMR structure with the data that I gave you?
It's open now.
Not this, so it's common, it's common. Yeah. I was.
Yeah, I don't think that was actually
It's 3. There's 3 unsaturations, so it's 2 plus 2 times the number of carbons minus the number of hydrogens. There's no nitrogens, there's no halogens, there's no oxygen. Well, so the oxygen doesn't count, divided by 2. So you should get 22 minus 16, which is 6 divided by 2, which is 3 unsaturation. You're welcome.
One is 11. Three is 11.
like a lot of boy.
Right? 1 minus 15. Yes. One.
So there's some money.
And also look at the starting formula, right? You have 16 hydrogens and 2 oxygens. Whereas you only have 14 hydrogens and 1 oxygen. So what did you lose here? I heard it. Water, okay? So you did some type of dehydration. Okay, and you have NaOH and heat. So this should make you automatically think, what reaction? Adrian, aldol reaction. Okay, and it's most likely intramolecular.
Why do you say that?
Because you only have 1A. You only have 1 reactant, right? So, and it's big. It's C10H16O2. So it's not like 2 things are coming together to make C20, right? You're not changing the number of carbons, right? If you had more carbons in B, then I wouldn't necessarily think intramolecular, because the carbons is staying the same, right? You should think intramolecular. And I would also think you have some kind of open chain. Look at that. I mean, you have all of these CH2s. Yeah, no, I don't, sorry. I don't mind.
Do this, so now, this is the problem I had on the list test. I did all this, figured that out, but then I was like, okay. I'm gonna be honest.
One, look at where these are, okay, those are pretty far down. So I wouldn't say it's a CH next to the CH street, that's a dead end, right? You can't have multiple dead ends. But you have to have 3 degrees of unsaturation. You know, one of those is an aldehyde. It is an aldehyde.
It is.
Okay, 9.7 between 9 and 10. That's the aldehyde. So that's one end of your molecule. This is the other, this could be another end. So that one's a, right? Again, you have too many dead. So I would think instead of this being, because of where it is, I think that this could be another bond with 1 hydrogen. So it's not necessarily the CH3, but if this is in the middle of a chain, okay, these are okay, these would be in the middle of a chain. So look, where you only have a triplet CH2, that means you have to have something with no hydrogen next to it. So that would be a good place for a carbonyl.
Okay.
It's like a ketone.
Well, it is,
Okay. I like to plan it out, but then put the together, but it might, if you struggle to go from this to the long line, when you're planning it out, write it out. Like, so, like, this one here, this would be that, right? Let me just change my colors. I'm gonna get smushed. All right, so that would be one end. And so like here, I would say this is a CH2 next to a CH3. So then what I would probably do is say, okay. CH2. And then kind of start. Oh, okay. Okay, thank you. All right, let's work through this a little bit. So the first thing that you should realize, all right, we did the unsaturations. I said you had 3. Okay, so if you don't have that formula known, write it down. You're allowed to have your notes. Okay, so that aldehyde, bring an NMR table or look up an NMR table. You know, when you have the NMR problem. All right, so between 9 and 10 is singlet. That's 1 hydrogen. That's that aldehyde hydrogen. Okay. All right, you have a quartet, that's 1 hydrogen. The significant thing here, okay, is this chemical shift at 5.5. All right, so I mean, maybe I'm taking this for granted, all right, but part of us doing NMR in lab, right, is so that you can take that practical aspect and apply it in lecture. Right? When you have resonances that are between 5 and 7, it's typically a hydrogen off of a double bond. So that's your vinyl hydrogen. Okay, you can't keep having, it can't just be these CHs next to CH3s. It's gonna be too many dead ends. You have to have a chain here. Okay, so I would think that this is a CH where you have 2 and 1. Just because, again, just the nature, you have to have a chain. Like there's too many, you don't have enough unsaturations to make it a ring. Right? And it's going to be an intramolecular reaction because the number of carbons isn't changing. So I would just think open chain. And it's got to be some open chain that can form a 5 or a 6-membered ring. Okay? Understand, you're never really going into, like when you go into lab, right? And I have you do an NMR in your compound. For the most part, you're not going in, well, maybe some of you are going in completely blind, okay? But you really should have a rough idea if you at least looked at the board of what you made, okay? Even if you were to do an experiment where you were identifying an unknown, okay, you would do chemical testing first to know like what you had. You wouldn't just stick your tube in the NMR and poof, you know, I'm gonna figure out the structure. You have to have some other information, okay? So use the information that you have, right? Use the fact that this is a dehydration reaction. So again, aldol, all right? You have 10 carbons and then you still have 10 carbons. So we're not adding anything to this, but something must have reacted internally, right? All right, so then 5.3 again, so you have this other 1 hydrogen. So again, I would think it's that kind of like CH. And again, there's got to be a double bond somewhere, okay? All right. Then we have we have 2 hydrogens. It's a triplet. So it's just a CH2 next to a CH2. So you got to think, sorry, I shouldn't put the double bond there. You got to think one end is blocked, okay, where there's no hydrogens on that carbon, okay? And the other end has got to be blocked, right? Because, well, not necessarily. One end is blocked, okay? Then you have another one of these. All right, so let me block that end. And then we have this again, you just have a CH2, that's a triplet. So one end has to be blocked. Then we have another CH2, that's a quartet. Okay, so I think CH2, again, there's 1 hydrogen and probably 2 hydrogens. 1. All right, I started putting pieces together here. So I figured that methyl group would be one end and the aldehyde is the other end. All right, so.
Why did you put the double bonds in the second and third one again?
Because they're so far downfield that 5, there's got to be, they have to be attached to carbons that are on the double bond, okay? All right. So that when you put this together, if I have that CH3, CH2, and I know that because that CH3 is just a triplet. Okay, but that, oh, did I? No, I didn't. Okay. So then you could have CH, CH2, CH2. And then I'm gonna I have to shift this down. I'm not gonna fit it. I'll do it as a bond line. Okay, it's a long chain. I'm not gonna give you something this hard, okay, as far as your chains go, but I want you to be prepared to try and think your way through something like this. Okay, so then if we do it as a bond line structure. Five, 6, 7, 8, 9, 10. Okay. All right. So there's my structure. Now I got to figure out how this thing reacts. You have alpha hydrogens here here, and here. All right. I'm only going to lose water here. If you look at this NMR data, I'll go back, but you can see the structure down at the bottom, okay? Right, you clearly still have that double bond. Right? Those hydrogens did not go away in the NMR. What did go away in the NMR? What don't we no longer have in the product NMR? The aldehyde hydrogen. Okay, so there's no aldehyde hydrogen anymore. So what that most likely meant was that was the carbon that got attacked. Right? Remember when we were doing the aldol reactions, your enolate attacked the carbonyl. So which one would be able to give us some type of 5 or 6 membered ring if we deprotonated? The purple one, the blue one, or the green one? Purple one, right? That's the only one that could give us the right ring. Okay, so if we do this mechanistically, okay, I'm just going to write this over just so that we have a nice, neat mechanism. Okay. Here is my alpha hydrogen. OH minus takes the hydrogen. The electrons go on to the carbon. My enolate is going to attack my carbonyl. My electrons go out onto the oxygen. One, two, three, 4, 5. One, 2, 3, 4, 5. On carbon 1, I have to have the chain that's still there. On carbon 5, I have an O minus. On carbon 2, I have a carbonyl. This is aqueous, so I can protonate my O minus. I still have an alpha hydrogen here, and I still have base. So I can deprotonate, the electrons go in between, I kick off the OH group. Right, and there's my product. Again, I'm most likely not going to give you a molecule that's that complicated from an NMR perspective. Okay. But you need all of that for the mechanism. Remember, with your mechanisms, it's the electrons that move. So you're moving lone pairs, okay, or pi bonds, or just bonding electrons. Do we have any questions with this? What I'm gonna do, okay, and again, so this is the thing with your mechanisms, right? You don't actually have a ton of mechanisms to choose from here. You're looking at your Aldol mechanism, which could take the form of a simple aldol. That's when you're reacting with yourself. And then remember, if you're reacting with yourself, right? If the example is something like this reacting with itself, the product will have more carbons. You can have your crossed aldol. No, sorry, we did directed first, I think. The directed aldol reaction, that's where you have an excess. So you have this one can only form the enolate. And then you have an excess of something that can't form an enolate. Right, and again, your product will have more carbons. Right, then we had our crossed aldol, and then that's where you used LDA. And again, your product, well, it depends. All right, if there's more carbons, okay, it was two molecules reacting. So those are your aldol mechanisms. Then you had your Claisen, and it was the same thing, but with esters. But no dehydration. And then you had the Michael reaction that we did last week. Okay, and that was when you react with the beta carbon. Mm-hmm.
Can you give me some of the Michael reaction?
Mm-hmm. Okay. So here we have your diketone and you have an alpha beta unsaturated ketone. I mean aldehyde. So there is no H alpha here. And this is the most acidic one, right? Because it's between the two carbonyls. So your OH minus is going to take this hydrogen. The electrons go on the carbon. Okay, so now we have our enolate. So this enolate is a weak nucleophile. So instead of reacting with the aldehyde carbonyl, it's going to react with the beta carbon. All right, so just to kind of keep track. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I need a double bond between 3. No, between 4 and 5. Okay. So I have that. And then we can protonate. And what do I make? What is this here? Good, an enol. And so to finish the mechanism, you can just say it tautomerizes. To the ketone, I mean to the aldehyde. So that would be your Michael reaction. And we stopped there. We didn't go on to that Robinson annulation that's talked in the book. We will, but we're just going to stop the reaction there for now. Caroline.
Will the nucleophile always look like that? Like the.
If it has the option of reacting with the weaker with the weaker electrophilic site, then yes. Okay, so what we'll do after next week, this can go on and react some more, where you get you make another enolate, but now it's reacting with the carbonyl. Okay, there we are. You don't have an extra carbon energy. I mean, 1, 2, 3, 4. I did. But where did I add it? 1, 2, 3, 4. Wait, did I? Why can 1, 2, 3, 4, 5 here? 1, 2, 3, 4. Why am I not seeing the difference? Oh, I went down and up. Okay, so 5, yeah. One, 2, 3, 4, 5. Okay, the product's okay though. Yeah. You know. How about a synthesis problem? I'm writing another one down. Glassy. All right, let's look at the first one. Let's just see if we can find the starting material here. So if you look, you have 1, 2, 3, 4, 5, 6. Let's see. 1, 2, 3, 4, 5, 6. All right, so there's the starting material. But we have 2 alkyl groups here, what look like 2 alkyl groups here. All right. One thing that we could do is we know that we can add. How can we add alkyl groups? How do we add carbons? What reactions do we do? Yep, with what? But no, what does the Gilman react with?
What does it react with?
Yeah. Yeah, so you can, so Gilman's can react with acid chlorides or the alpha beta unsaturated ketone. Well, that would be like a better way to go because we have an OH in the starting material and we also have an OH there at the end. Okay, so if, all right, you take this and how to get that OH, you could have done lithium aluminum hydride, water, or you could have done NaBH4. And that would take us back to that aldehyde. Okay. All right, so if we had added, if you look at that aldehyde, this would be beta, right? So that you could have alkylated there. You would have added this Gilman reagent. Hold up. Wait, actually, before I do that, all right, before I go to the Gilman, I have to figure out how I alkylated with this ethyl group here. So that we could have just added by doing LDA and ETI. Then that would take us back to this. Okay. That we could have gotten, and I'm running out of room, by reacting with the Gilman reagent. That should be a 2. I'm just going to go up top here because I am running out of room. All right, so that was your aldehyde, and that aldehyde you got by doing PCC, okay, on that alcohol. All right, so that's the only old reaction, right? That's the only old thing that you would have to know, and the reduction, but we've been using them. So your first step would do PCC to give you the aldehyde. Then you could react the Gilman reagents. Okay, and then you'd have to add water. Then in step 4, you could do LDA to deprotonate the alpha carbon now. And you can add your ethyl group. And then we can just do the reduction, either again with sodium borohydride or lithium aluminum hydride, either one. Okay. Do we have any questions with this one? All right, so again, I'm going to keep the synthesis mostly posted. I'm not going to pull from the fall. All right, so like your other synthesis problems were fair game. All right, really, I won't probably, I know I gave you some practice with doing with a benzene ring, right, with an acid chloride. I feel like on one of your practices, we did that acylation of a benzene ring. Okay. So just, it will be just this semester, and it will be primarily focused though on this chapter. All right, let's look at this next one. Let's just count carbons. Right. You have 1, 2, 3, 4, 5, 6, 7. All right, and then you also have those ethyl group carbons. We have a 6-membered ring. Okay, so you have 8 carbons here. So we clearly did some kind of transformation. But if you look, all right, the ring is coming from that carbon chain. All right. So you have a couple of strategies that you could do here. Look at where those methyl groups are, right? They are alpha to that ketone. So I would think at some point, actually, I wouldn't even do it as a retro arrow, just to show you that there are different ways to do this. At some point, you had to use LDA and methyl iodide. If we look at this starting material, we also had to have hydrolyzed the esters. All right. So if I look at this, I would probably say I'd actually start in the forward direction here and think about how to make an enolate, right? And so I would have said, all right, NaOET. Because it's symmetric. And there would be my enolate. Well, this leads me to be able to have that intramolecular attack, and then I can get rid of one of those ester groups, right? Because this can just attack here, and I have a leaving group. So my step 1 would have been NaOET. So let's just draw that product that results from that. Okay. This comes down and that leaves. So just by adding NaOET, I'm left with this. All right. Well, how, right, do we get rid of this? It's not present anymore, right? But when we did these reactions, if we looked at, sorry, my marker. You remember what this was? That acetoacetic ester? What happened when I did that? Joy. Right, you got that rearrangement and we were able to hydrolyze the ester and then decarboxylate, and you were essentially just left with acetone. And if you did any kind of reaction here, you had that substituent. Remember, we were alkylating that position and then we did that whole decarboxylation. Okay, so our first step, we added NaOET. So now let's hydrolyze that ester and get rid of it. Or, oh, actually, let's wait on that. Instead of hydrolyzing the ester, let's react at this position. Let's alkylate there, right? That hydrogen's acidic. So let me add some more NaOET. And then I'm going to add a methyl group. Right now, I can heat. Sorry, I can do NaOH. I can do HCl, and now add my heat. And I'll get rid of that ester. Just gonna move this. It's not there. Okay, now how much LDA do I need to add to alkylate that position? Grace?
1.01.
Yep, you just need a slight excess because you want the kinetic enolate. And I add my LDA, I mean my methyl group. So if I write this in the forward direction, I have my NaOET. I would add just some water to keep it protonated. Then I would add NaOET again. Add my methyl iodide. Add my base. Add acid. Heat it up. Add LDA. And then add methyl iodide. So that's the synthesis completely based upon what we've done.
So
AJ.
that last step, can you just explain, please, why
Oh, I
it
need-
adds to that carbon?
Oh, because you have two carbons here. You have the more substituted and then, oh, sorry, I should have probably just change that color. So you have the pink one that's more substituted and the green one that's less substituted. So you can either do the kinetic or the thermodynamic enolate. So 1.01 gives you kinetic. And then 0.99 gives you thermodynamic. Okay. All right. So we'll do more practice tomorrow in recitation. Okay. One of two things will happen this evening. Either I will post even more practice, or I'm gonna get a nice roadmap up for you guys to use on for the test. Okay, so I will figure that out later this evening.
Okay. Hopefully with Senator, the worst case you do tomorrow night.